Howdy.
Professor Li. So Professor Hao Li received his first and master's degree in chemistry from Zhejiang University in 2005 and 2007, respectively. He completed his PhD at Northwestern University in Chicago in 2013 under the supervision of Nobel laureate Sir Fraser Stoddart before carrying out postdoctoral research with Professor Jonathan Sessler, the University of Texas in Austin. Since 2015, he has been a tenure-track professor at Zhejiang University in Hangzhou, and is a specialist of the dynamic covalent bond and its use for self-assembly in water. And the title of his talk is Dynamic Covalent Chemistry in Water. Please.
Thanks so much, Mr. Chairman. Can you hear me clearly?
Yes, I can hear you perfectly, and I can see you a slideshow perfectly as well. So everything is fine. Thank you.
Okay.
Just let me tell you something. We deactivate the cameras just to save some bandwidth for the next speakers. So I deactivated all the personal cameras, which basically do not bring anything to the discussion, and in order to privilege the screen sharing and voice. Okay, go ahead.
Okay, so today my story will be dynamic covalent chemistry in water. So this is a symposium of non-covalent interaction. So I don't really have to introduce the so-called pi-pi stacking or donor accepting interaction. Basically, we have a electron-rich one and the electron-deficient one, which is a biology. They undergo pi-pi stacking, so charge transfer will occur. So from the donor to the acceptor, you can see this is typical pi-pi interaction, donor accepting interaction. And more recently, actually, you can see pi-pi interaction also occurs between aromatic radicals. You can see. So we have a radical here. So it is a origin. We do reduction. We can get a paramagnetic radical. So if we cool down the temperature to minus 110 degrees, so you can see the species will become EPR silent. So in the beginning, many people propose it will have this reaction. So you can see this radical electron undergo bonding formation to get a covalent bond. However, after we get a single crystal, we know that this is not true. The truth will be the stomol orbital of the radical undergo pi-pi stacking, so to undergo spin pairing. So in this way, so this is because in this form we can avoid this. In the covalent bond formation, actually we destroy the aromaticity, and this one we can keep the aromatic compound here. So actually, a few years ago, so one of our senior colleague, Professor Zhejiang Li from Fudan University, published a review paper telling us that pi-pi stacking, between two identical radicals are a general interaction. You can see bipyridine, naphthalene diimide, TTF, and the porphyrin. You can see they all undergo pi-pi stacking to get spin pairing interaction. So my question will be, so if two identical radicals can undergo pi-pi stacking, can we do the pi-pi stacking between two different radicals? So, hetero radical pairing interaction are not reported before. So you can see this is a NDI, which is naphthalene diimide. This is viologene radical cation. So can they undergo pi-pi stacking? In the beginning, you can see the SOMO orbital, they do not match, right? You can see the face. This is plus, plus, minus, minus. This is minus, minus, plus in the middle. So, the overlap should be very weak. But remember, this radical is anionic. This one is cationic. So they have Coulombic attraction. So if we can take advantage of the Coulombic attraction, maybe even although the SOMO orbital overlapping is very weak, we can still get the pi-pi stacking. Let's see. So this is the deal. So my students buy this compound, we do the reduction. This is a typical absorption spectrum of the viologene radical cation. And we synthesize a naphthalene diimide with glycol chain for solubility reason. And we also did the reduction. You can see this is typical radical NDI. And my students mix these two species together, and they are rarely depressed. There's no, switch of the absorption. So if you mix them together, you will get just an, overlap of these two species, and which means there is no pi-pi stacking. But I told my student, hold on, why not connect the bipyridine radical and the naphthalene diimide radical together by a linkage, by a covalent bond. So the entropy loss will be ruled out. And you can see we did the absorption spectrum again. You can see we have the nice near IR band. So normally if you have this nice near IR band, which means the electron undergo delocalization, they will have a large room to move, right? To do the movement. And this is a good signal for pi-pi stacking. And we did the EPR experiment. You can see this bipyridine radical is paramagnetic. This one, naphthalene diimide radical, is also paramagnetic. But if we combine these two species together, at room temperature, you can see this EPR signal is pretty weak. So this is because upon occurrence of pi-pi stacking, they become diamagnetic, right? If we cool down the temperature to minus 30 degrees centigrade, you can see the EPR signal disappear totally, right? If we raise the temperature from minus to plus 75 degrees centigrade, you can see the nice EPR signal will appear, right? This is because pi-pi stacking is always unfavored in terms of entropy. If you raise the temperature, entropy will drive the pi-pi stacking to free, radicals. So after we get this heteroradical pi-pi stacking, we use this new novel interaction for host-guest chemistry. So we get a macrocycle and a guest. This macrocycle is blue box, first developed by Stoddard. And even although there is no covalent bond connected the macrocycle and the guest, we can still get this pi-pi stacking because remember, in the macrocycle, we get two species, two radical cation, and they can do the pi-pi stacking simultaneously with the guest. You can see we get this nice near IR band. And we did a control experiment. You can see if you use a stopper, right, to block the threading, and you can still get the radical anion and the radical cation, and there is no pi-pi stacking band here. So this is a signal that this band is a result from host-guest complexation. And we use this method to get a molecular switch. So in the beginning, the macrocycle is electron deficient. If it is electron deficient, it will get a electron-rich friend by pi-pi stacking donor accept interaction. And if we reduce the macrocycle and the naphthalene diimide to the radical, and then the radical macrocycle will find a new friend, they can do pi-pi stacking with another radical. You can see we can also use the CV to see this is totally reversible. So to sum up, so normally in the field of supermolecular chemistry, we get donor accept interaction. This is more like the interaction between a hot lady and a cool guy, right? This is typical pi-pi stacking. So for this one, this is pi-pi stacking between two identical radicals. They have similar SOMO orbital, similar background, similar education, similar religion, and they can do pi-pi stacking. This pi-pi stacking is not as often as this typical pi-pi stacking, but for this one, we get two different radicals, right? They have totally different SOMO orbital, their background, their religion are totally different. But because of the Coulombic attraction, we can still make this pi-pi stacking occur. So here is the problem. So students want to publish a paper, but students they do not want to run columns, right? So for example, if actually we synthesize this compound using 1 year to do the synthesis, this is because this synthesis rely on irreversible bond formation. So if the bond is irreversible, which means we have byproduct. For example, if you want to make this macrocycle, you can see we can make this compound. We want to make the blue box, but actually we get a mixture of all kinds of oligomer polymers, and then we have to run Conan, right? We have to use a template, and we have to remove the template. This is just like a pain, right? So how to avoid this Conan thing? So we have dynamic chemistry. So if this reaction is reversible, right? If we can do a reversible reaction and we can design a compound which is the most thermodynamically stable one, and we can synthesize this compound, maybe in some situation in quantitatively yield. So this is the case by using imine chemistry. So this is our first paper in the field of dynamic covalent chemistry. So basically amine and aldehyde, and they can undergo reversible reaction to form an imine compound. So that is what we do. So here, so we buy a compound which contains 3 amino units, and then we synthesize a compound which contains 3 aldehyde units. If you mix these 2 species together, and after 8 hours, we can get a tetrahedral compound in 99% yield, which means there is no byproduct. And actually, so we ask ourselves why this yield is so high. So is there any reason why this compound is so stable in terms of thermodynamics? The answer is yes. You can see if we get this compound, the yield is very high, 99%. If we remove the methyl group here, the yield is a little bit lower, in 90%. If we functionize this unit with ester and methyl oxyl unit, the yield is still high. However, if you switch this benzene ring to triazine, there is no cage formation. And also, if you replace the proton here with a methyl, oxyl, and fluorine atom here, no cage compound. So why? What is that? Why is this proton is so important? This is because this cage is driven by CH pi interaction. Remember, so this proton is electron deficient because this carbon is sp hybridized, and this is plus this pi bond. This benzene ring is electron rich. We have CH pi, and also remember another proton has to undergo hydrogen bonding with this nitrogen. So you can see we have nitrogen bond here, which means both of this proton will undergo either CH pi interaction or hydrogen bond. So you cannot remove any of them. And also, if you replace this benzene ring with the triazine, which means this will become planar. If this is planar, which means there is no twisting, and then this proton will not point to the phenyl unit here, and there is no CH pi interaction. So which means you have to do the twisting, and you have to make sure this proton and this proton are both available. And then that is the reason why we can get the high yield of the cage. And we use this microcycle to protect a white phosphorus. Actually, this work is inspired by Professor Nitschke at Cambridge University. So you can see this microcycle is tetrahedral. We have a white phosphorus in the middle. And without the protection, you can see after a few minutes, the white phosphorus will be destroyed, will be oxidized by air. And with the protection of the microcycle, even after 3 months, we can still use solid state NMR to see the white phosphorus is very stable. So, and recently, my students use this method to make a cage which contains 4 radicals, and within the microcycle, the 4 radicals can undergo very weak spin pairing interaction, and we published this paper recently. Problem. What is the problem for imine bond formation? So normally, if you make a aldehyde and imine to get a amine and aldehyde to get a imine, which means you will release the water. The implication is very obvious. If the system contains a lot of water, and the equilibrium will shift to the side of imine hydrolysis, which means you cannot use water as a solvent, right? Normally, you can see we have many excellent examples of using imine chemistry to do self-assembly. For example, by Cooper, by Professor Kim King, by my colleague Cao Xiaoyu at Xiamen University. They all use organic solvents, typically chloroform as a solvent to avoid water. So if you cannot use water, you will have a problem, right? So if you have organic solvent, which means the organic solvent will occupy the cavity of the cage, and then there is no host gas chemistry taking place here. So in most of the imine cage, you will see we get many beautiful cages and they are useless, right? So because in the middle, we have organic solvent. So the central question is, how can we use water to do self-assembly based on imine? So actually, we do have the method. So normally in the field of inorganic chemistry, we have an effect, so-called kinetic effect, which means if you have a bond which is labile, so for example, this imine bond is very labile in water, but if a system it contains multiple imine, and then this system will be stable, will be more stable than the single bond. We call it as a kinetic effect, right? Actually, we have this. Everywhere. So a Chinese old saying told us a single chopstick can be easily broken. With 10 of them tightly bonded, they can withstand much more damage, right? This is an old story from a father who is dying, and he told his sons not fighting. They should stop fighting. So they use this story to persuade their sons to become friends, right? So this is the same mechanism as the kinetic effect. So we use this one to do self-assembly in water. So for example, my student Yixin Chen, so she bought this compound which is water soluble, and we have this triamine. If we combine these two species in water, you can see the imine will be killed by water, so, right? You can see this compound, they are not even though absorbed in NMR spectrum. Only trace amount of this compound can form in water, just because this bond is too labile. But if we synthesize a trace aldehyde and this trace amine, we combine this in pure water, and we can get this microcycle in 80% yield. You can see this is a nice NMR without purification. You can see this is the proton C, which is just undergo CH pi interaction with this phenyl group. That's why it is so shielded, right? Upfield shift. And you can see, because this occurs in water, we can take advantage of hydrophobic interaction for host gas chemistry. So you can see many host gas can be recognized by this microcycle in water. For example, hydroxystein and pyridine benzene, right? If the size is complementary to the microcycle cavity, they will be recognized because of the hydrophobic interaction. And if the gas is too big, there is no gas recognition. Actually, we published this paper recently, and also remember this microcycle, because of the CH pi interaction, and then this microcycle become actually cage become chiral, right? You can see each corner can be, this is anti-clockwise, this is clockwise. So which means they are chiral, they are enantiomers. We can use the chiral HPLC to do the separation. We can separate this compound, do the CD spectrum. You can see the nice image, mirror shape spectrum, and so which means these two species are totally chiral. So if it is chiral, which means if we use a chiral template, and we can drive this cage, enantiomer selectively. So if, for example, if you add this chiral gas, maybe this enantiomer will be more favored than the other one. If you switch the template to its enantiomer, and then we can drive another cage enantiomer, drive its formation, and this enantiomer will be more favored than this one, right? This is just a so-called gas-induced, chiral self-assembly. And you can see this is the case. If we use this gas, we get 1 enantiomer of the microcycle. If you use this gas, we get another enantiomer of the cage. And actually, both gas is CD silent, right? Because they do not have absorption in the UV region. And also, in our recent paper, we also use this multivenous, this Kinetic effect for self-assembly in water. You can see we synthesize a compound which contains 6 aldehyde, and this 6 aldehyde mixed with a amine compound with 2 amino units. If you mix them together in water, the yield is 60%, and in acetonitrile, the yield is close to quantitatively yield. This is because acetonitrile is a template. This is the nice NMR without any purification, just crude NMR. You can see this is a single crystal, right? You know, when we get a single crystal in acetonitrile, you can see the acetonitrile will go inside, act as a template. In water, we will get a so-called pseudo amputee cage. So just because the water cannot be the template. Also, if you use S diamine, we get this S-shaped cage. If you use the RR diamine, we get this enantiomer. If you use the rhythmic mixture of the diamine, and we get a rhythmic mixture of the cage, which means we have a narcissistic self-sorting taking place here, which means all of the S diamine will go to the cage here, and all the R diamine will go to this cage. You can see this nice mirror-shaped CD spectrum here. And also because of this cage is water-soluble and compatible with water, we can do the water-soluble host-gas chemistry here, right? By using the NMR titration, we can get this dibromo ethane here. You can see the binding constant is 10 to the third. And you can see we can bind all kinds of gas here just because of water. Without water, we also did titration in acetonitrile. There is no binding. Just the water is very important here. And also, just because of the host gas chemistry, we can use this chiral microcycle to separate the chiral gas here. You can see by using the this is, I think, the SS cage. We can selectively bind the R isomer of the gas and leave the S isomer, not binded here. You can see. So as I mentioned before, we use multivenous to get the imine very stable. Another method to make the imine more stable is to do substitution. So what is substitution? You know, normally if you see why the imine is so unstable, is just because of the resonance structure. You know, after conjugation, this imine bond takes on plus here, minus here, right? Which means, you know, water, the oxygen, the oxygen is negative. Of course, the oxygen would like to bind with the imine to form to do the imine hydrolysis. But if we do the nitrogen substitution, we switch the imine to a hydrogen, right? This is a hydrogen. The hydrogen will undergo electron delocalization. The hydrogen will move the electron from the nitrogen to the carbon here to make this carbon negative. If this carbon is negative, which means this carbon is less electrophilic, and then the water would unlikely to come here to destroy the imine bond here. So this is what we did 6 years ago. So we synthesized a water-soluble hydrazide, and we synthesized a water-soluble aldehyde. And if we combine these two species in the beginning, we get the polymers. But if we heat this mixture together, and we will get the catalyst in quantitatively yield. So you can see this is the NMR. You know, because this NMR is very dilute, we use a very dilute solution. So we zoom in. We do have many small peak, but remember this is the spectrum. We zoom in and not. You can see we can still get this nice NMR, and you can see this is the mass spectrum, which is just the crude sample. and this is a single crystal. And you can see in the beginning, we have the starting material. And in the beginning of the self-assembly, we get many polymer and oligomer. You can see we have a peak here, we have a broad peak here. And after hit the electron, after 8 hours, you can see the catalyst is the only product we can observe. And the driving force, what is the driving force? This catalyst is totally driven by hydrophobic interaction. If you add organic solvents, for example, acetonitrile, DMSO, or methanol, and then this catalyst will undergo decomposition, we can get this microcycle and oligomer polymers. And if we remove the DMSO and we add water and we heat this system, we can recover the catalyst. And a few years later, we use this method to synthesize macrocycles, just because the hydrogen condensation is reversible, and we get this macrocycle in close to quantitative yield with a template. And by using the counter-anion exchange, we can remove the template, and we get the macrocycle as the chloride salt. And remember, this macrocycle is soluble in water, and we can use this macrocycle to do host gas chemistry. And this phyllanthropine is not water soluble. Anthracene is also not water soluble, and this solid can be suspended in water. We use this macrocycle to solidicate the solution. We can see this macrocycle only recognizes phyllanthropine. This is because this macrocycle has a bent cavity, and this is linear, right? Because the bent host would like to bind with the bent guest, and we can see this can bind the phyllanthropine selectively and leave this not soluble in water, and we can do separation. Finally, we use dichromazane to extract the gas from water to solvent to organic solvent. We can reuse the empty gas for another cycle for the separation. And after a few cycles, this hydrogen will undergo exchange, and we can get oligomer polymer. Another method to make this bond even more inert is to replace this nitrogen to oxygen. So you can see we use oxide to do the self-assembly, and then this bond is even more stable. So because this oxygen is electronegative, and which means the basicity of the imine bond here is even lower, right? And then if this is not basic, which means in water, we cannot protonate this imine bond. And then there is no imine, bond formation. Without this NH imine, and then this bond is super stable. You can see, normally if you synthesize this catalyst, if you switch the solvent from water to organic solvent, this compound will die, right? Will decompose. But if we synthesize this compound in water, and then we change the counter-anion, and then we dissolve this compound in organic solvents in acetonitrile, we can see this compound is super stable in organic solvent, even without driving force, because this bond is chemically inert, just because of this oxygen. And recently, we use this method to synthesize a cage. You can see this is a protected hydride, this is a aldehyde, and then we mix these two species in water, and we use acid to remove the acetone protecting group, and this acid will catalyze the imine bond formation. Finally, we can get this macrocycle in 50% yield, and after counter-anion exchange, we can get a pure compound. So this cage, has a long cavity, and we found that this macrocycle is able to recognize a 2-chloride minus, in the cavity. You can see in the beginning, because there is no gas template, this macrocycle is flexible. You can see the peak is pretty broad, and after we add chloride, you can see a new peak taking place here. So if you add one equivalent of chloride, you can see all the broad peak become sharp, and the NH will shift all the way to the 12, right? This is a typical, I mean, a downfield shift, indicating the occurrence of nitrogen bond. And if you add another equivalent of the chloride, you can see another peak, I mean, set of peak taking place here. And this F and G, you can see these two species will undergo hydrogen bond with the chloride. You know, hydrogen bonding always drives the chemical shift from the upfield to the downfield. And we can use the NMR titration to get the binding constant. The K2 is 10 to the 5th. Also, you can see the binding has selectivity. You can see if you have one equivalent of the chloride, one equivalent of the nitrate, and we have 4 choices here. We can get the chloride, nitrate, nitrate, chloride. We can also get chloride and 2 nitrate. But actually, by using the NMR, you can see this will be the major species. You can see this NH is more like this compound, right? Because this mixture of this NH is very similar as this NMR, just because in the bottom part, it is a chloride. And you can also see, you know, the F proton here is very similar as this species. You can see just because in the top part of the cavity, we have the nitrate. You can see this F is pretty close to this one. I mean, is very different from this species here. So which means we can get a double selective heterodimer complexation in the middle of the cavity of the cage. And we also get a single crystal. You can see because of the hydrogen bonding and the Coulombic attraction, we can recognize 2 chloride in the middle of the cavity. And this is a single crystal. So to sum up, so in our group, we focus on using the dynamic covalent chemistry to do self-assembly, so which is reversible. Because of the error checking and the self-correcting, we can avoid byproduct. And also, imine is very unstable, it's very labile in water, but if we have many imines, and the system will be more stable. So in China, we have a famous saying, right? So every business can be done by 1 banquet. If not, use 2 banquets. You know, we have the same, mechanism. And also, if we have substituted imine, which is oxide and hydrogen, and then they will be very stable. They will be more stable than typical imine in water. And we can use this new method for self-assembly in water. So after that, we would like to thank all of my students who most of them are hardworking, and I just come here, give a talk, and they did all of the work in the presentation. And I also wanted to thank my university and the NSFC and the Zhejiang NSF for the funding support. And also thank you all for your attention.